Okay, so let's get started. So turn on your video as long as you have a camera. Okay, so there are several things to do today. So first one, we have to finish the chapter 1. So we have the 3 contents. The one is the continued discussion of the force of interest, that is the momentary interest rate. So the interest rate is usually given for a specific time period, such as year or a half year or month. That we think about the continuous, the interest rate that is more convenient theoretically. And the second one is a review on the Taylor expansion. So for example, e to the power x is approximately equal to 1 plus the x over, sorry, the 1 plus x plus the x squared over 2. So that kind of approximation is useful to approximate some interest. And the third one is the equivalent rates. For example, the 3% nominal rate compounded monthly is approximately equal to 3.05% annual effective rate. So that we define the equivalent rates, and we do some examples. And after that, we do a weekly quiz. So the homework was given last week, and this quiz is based on the homework, while the question itself is not the same as the homework. So at least we use the same concepts, but not the same questions. And then we start at 11, and the quiz will be available at 11 in Canvas. So you can see the quiz online and either print out or just see it on screen and write your answer and take a picture of it with the cam scanner in your iPad or iPhone or any smartphone or tablet, and then submit it by 11:30. I will be here until 11:30 to answer some questions. So in the following weeks, probably it will be just the 15 minutes or 20 minutes, but this time it's the first time, so I will give 30 minutes. Okay, so do you have any questions from last lecture or quizzes or homework? Okay, so if not, I will start. I will continue chapter 1. So yeah, so the last time that we started force of interest. So remember that if we have discrete the interest rate, that we define the I sub t plus 1 as a of t plus 1 minus a of t over a of t. So here a of t is the accumulation function. So this represents the amount you have at time t, and a of 0 is equal to 1. So suppose that at t is equal to 0, you have $1. Then what's your account balance when the time is t? That is a of t. And the interest, the I sub t plus 1, is defined by this. So previous terms principal as the denominator, and the increase from t to t plus 1 is the numerator. Okay, but the force of interest is continuous one. So suppose this a of t, the increase continuously like this figure, then we define the slope at t naught as the force of interest at t naught. So the definition, the delta t is the dA dt over at. So you can see that the denominator still we have the same one, but the numerator basically we have the very small increase, so that we take the derivative at time t. So we can also write the a prime t over a of t. And also we have the amount function, capital A of t. So this is the same as lowercase a of t, but the lowercase a, we have a rule that the a of 0 is equal to 1, but the capital A, it can be any number. Okay, so suppose that the a of t is equal to 1 plus 0.2t, that is 20% simple interest. So $1 becomes $1.20 a year later, and $1.40 2 years later. So then, for example, that we can calculate the delta 1 as a prime of 1 over a of 1. So a prime of 1 is 0.2 because the you can see a of t is just a polynomial, the first degree polynomial. So derivative is 0.2, and the denominator, the 1.2, so 0.1667. So you can see that the $1 becomes $1.2 after a year, and this becomes $1.4. So yeah. Yeah, so a of 1, yes. So here that we increase the 20%, the amount increases by 20%, but here it only increases by smaller amount, so 0.2 over 1.2, so 16.7%. And actually, the delta 1 is the a prime 1 over a of 1. So that is the 16.7% approximately. Okay, and then we have a formula. So if the force of interest, this derivative is given, certainly if we integrate function, that we can calculate a of t. So from delta t, we can calculate a of t. And that formula is this. A of t is exponential of integral 0 to t, the delta r dr. So the proof is here. So basically that we start with this, and the idea is that this part is just the derivative of log of 80. So we integrate both sides. Then you can see that some term vanishes, and after taking the exponential of both sides, the a of t becomes this one. And maybe it's more convenient to memorize this one. So a of t2 over a of t1. So that means the how much the amount increased during the time period t1 to t2. So that is exponential of t2 over exponential of integral t1 to t2, the delta r dr. Yeah, anyway, so this is the ratio of these two. So immediately that you can get this. So it's a corollary of the original theorem. Yeah, so, and the last time that we did one example with this. Yeah, so that we start the next theorem. Where is that? The page. Sorry, I have to at least see the statement. Yeah, so we are thinking about the relationship between the effective rate and the force of interest. So effective rate and the force of interest. So if the delta t, the effective rate of interest, is equal to log of 1 plus I, then the effective rate of interest is I. So if the force of interest is this, then effective interest rate is I. So this is the correspondence between the delta t and I. So the effective rate of interest is I. That means A of t is equal to the 1 plus I to the power t. Yeah, so how to prove this? So this comes from the previous theorem. So A of t is the exponential of integral the 0 to t, the delta r dr. So this is actually, if the delta r is log of 1 plus I, then exponential 0 to r, oh, sorry, sorry, delta r, maybe, okay, so maybe I rewrite this. So delta r is always log of 1 plus I, so I rewrite this as the exponential 0 to r, exponential integral 0 to r log of 1 plus I dr. So this is constant in terms of r, so this is just exponential of, so 0 to t, so t times log of 1 plus I. So I would say that the, oh. Exponential of this. Okay. So this is just a 0 to t of constant, so constant times t. So then exponential of log of I plus 1 is just I plus 1. So exponential and log are inverse function each other. So this is 1 plus I to the power t. And this is the end of the proof. So yeah, you can remember that the this log of I plus, log of 1 plus I is slightly smaller than I, because you can see that if we write the function, the y delta is equal to log of 1 plus I, that is, sorry, this kind of function. So this is the delta is equal to log of 1 plus I. Here, x-axis is I and y-axis is delta. Then you can see that if we have a tangent line to this one at, sorry, the origin. Okay, so this tangent line is delta is equal to I, right? So the slope at the I is equal to 0 is 1. You can just differentiate it. So that you can see that the log of 1 plus I is always slightly smaller than I. Yeah, so maybe some examples. If I is equal to 0.05, then delta is equal to log of 1 plus 0.05. So this is equal to the 0.0488. And if I is equal to 0.1, then delta is equal to log of 1 plus 0.1. So this is 0.0953. So that means the force of interest is if 4.88%, then effective interest rate is 5%. So force of interest is momentary interest. So if the interest earns, interest compounds continuously, then basically 4.88% becomes 5% effective. And the difference between 5 and 4.88% is 0.12%. But if interest rate is higher, the difference gets larger. Difference between 10% and the 9.5% is equal to 0.47%. So compounding has more power if interest rate is higher. Any questions? So in general, the delta is lower than I. So this is true even if I is negative. You can see the graph. So one quiz based on this. And the next theorem, I have already mentioned verbally that if interest compounds many times a year, then that becomes force of interest. So I state this as limit m goes to infinity, I superscript m is equal to log of 1 plus I. That is, delta. So remember that this I superscript m means that the nominal rate is I, but it compounds m times a year. For example, what does it mean? 0.1 to 12. So this means the nominal rate is 12%, but the compounds monthly. So that means every month we have 1% interest. So 1% times 12 is 12%. So nominal rate is 12%, but the 1% compounds every month. So effective rate is higher than 12%, maybe 13%. Yeah, so limit m goes to infinity. The I superscript m is log of 1 plus I. So log of 1 plus I is always smaller than I, right? So if it compounds, the nominal rate can be lower to achieve the same result. Yeah, so we can write so this as I infinity. So if it compounds infinitely many times a year, then yeah, so that is delta. Yeah. Okay, so now the proof. The proof that is based on the definition of the number e. So limit m goes to infinity, I superscript m. This is equal to, by definition of I superscript m, m times 1 plus I to the power 1 over m minus 1. So you can check the definition of I superscript m. That is exactly this. So maybe you can remember this in the way that the 1 plus I is equal to 1 plus I superscript m over m to the power m. If we just do some algebra, this becomes this. Sorry, we have to take the limit still. Okay, m goes to infinity. Okay, so then what's this? So okay, so then we move this m to the denominator so that the limit m goes to infinity. Then okay, so numerator is just the same as the inside brace. So 1 plus I to the power 1 over m minus 1. Then we put 1 over m here. 1 over m here. Okay. Then actually this becomes ddx of 1 plus I to the power x at x is equal to 0. Okay. So this is because of the definition of derivative. So the right-hand side is limit the x goes to 0, 1 plus I to the power x minus 1 plus I to the power 0 over x. So this is the definition of the derivative on right-hand side, right? So this function. So we plug in x and plug in 0, and maybe you can say x minus 0 on the denominator. So x minus 0 over, sorry, 1 plus I to the power x minus 1 plus I to the power 0 over x minus 0. That is the derivative of 1 plus I to the power x at 0. Okay. And then what's happening? So you can see that the this x goes to 0. So this is the same as m goes to infinity when this x is the 1 over m. So you can see that this is just the definition of derivative of 1 plus I to the power x. Then what is this? So you can differentiate it. So this is the log of I, log of 1 plus I times 1 plus I to the power x. This is the derivative of 1 plus I to the power x. Then you can plug in x is equal to 0. Then the second factor becomes 1. So that means the entire quantity is log of 1 plus I. So you can see that if nominal rate I compounds the sorry, what does it mean? So the so I superscript m. So the nominal rate is what? The nominal rate is log of 1 plus I, then effectively that becomes I if the m is very large. So meaning the meaning of this theorem is if the interest rate compounds in arbitrarily small intervals, a nominal rate of log of 1 plus I makes an effective rate of I. Yeah. So maybe example. So suppose that we want suppose the effective rate is equal to the 10%. If the interest compounds continuously or compounds in arbitrarily small intervals, log of 1 plus 10%, that is what? You can see that the log of 1 plus 1 is 0.0953. So nominal rate of 9.53% achieves effective rate of 10%. Yeah, so this is the relationship between force of interest and the effective rate. Yeah, do you have any questions? Okay, so next one, we have the power series. So I don't know, when did you take the mass 2020? Last year, 2 years ago, 100 years ago? Anyone? Okay. So
2 years ago.
3 years ago. Okay. And Kenneth, what did you say?
Years ago as well.
Okay. And others, at least you have finished, right? So how many of you have taken mass 2030?
I did.
Okay. How many of you did not? 1, 2, Okay. So I don't know. Maybe. Okay. So the power series. I just review the examples of Taylor expansion. So several the examples. The first one, the e to the power x. This is equal to 1 over x over 1 factorial. That is 1. X squared over 2 factorial plus x cubed over 3 factorial, and so on. The factorial is the number. The product of integers from 1 to n. That is n factorial. So you can see that this is, the 1 factorial is 1, and 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, and so on. Okay. How about log? Often the log of 1 plus x is used in actuarial math. We have already seen in the previous slide. So what is the log of 1 plus x? If we approximate this by polynomial, what is the formula? I mean, the infinite sum of polynomials. Anyone? Log of 1 plus x is equal to what? What's the constant term, and what's the coefficient for x, coefficient for x squared and x cubed, and so on? Oh,
It would be
yeah.
1 plus
Yep.
x plus 1 over 2x squared plus, wait.
At first, you can see that the log of 1 plus x is this graph. So you can see the intercept is 0. And next term is x, right? Because this is the delta is equal to I. So the slope is 1. So the approximation by a linear function is x. So the first term is x. How about the second term? What's the coefficient of x squared?
1/2.
Close the 1/2, but we have the negative 1/2. You can see that the graph is like this, and the this is equal to 0. So the x is equal to 0. So at x is equal to 0, the slope is 1. But you can see that this is the concave downward, right? So that is, that we should have a negative something times x squared. And next term, do you remember the term of x cubed? Yeah, you can differentiate it. Yeah.
X cubed over 6.
No, actually this is 3. Okay, so this is different from exponential. And so it's natural to have factorial because we are differentiating it many times. But okay, so log of 1 plus x. Okay, so if you differentiate it, then what is this? So this is 1 over 1 plus x, right? Then log of 1 plus x and 1 over 1 plus x. This is the derivative, and we differentiate this again. So then this becomes negative 1 over 1 plus x squared, right? Then we differentiate it, then this is the 2. So 2 times 1 over 1 plus x cube, and then we plug in x is equal to 0. Maybe once more, negative 3 times 1 over 1 plus x to the fourth power. Then you plug in 0, then 0 and 1 and the -1 and this is what? This is the 2 and the -3. Then what the generally the Taylor expansion is f of x is equal to the summation of the f Taylor expansion at x is equal to 0 is like this k factorial over k, and this is the k times derivative of 0. So and k is equal to 0 to infinity. So the k is equal to 0, then this is just 0, so intercept 0. And the k is equal to 1, then the first derivative, that is 1. So we have the coefficient 1. And the second derivative, then we have 1 over 2 factorial, then -1, so -1/2. And the 3 factorial, then we have 2 here. Sorry, I think that this is 6 here, right? And the 6, yeah. And the next, the 3, yeah, so k is equal to sorry, the 3. K is equal to 3. The okay, so this is the x to the power k. So the k is equal to 3, then 1 over 3 factorial times the 2 times x cube, so that it becomes the x cube over 3, and so on. So the sign changes. So alternately, and yeah, then the number becomes just larger by 1, 2, 3, 4, 5. So this is log of 1 plus x. So this can be useful for approximate the some interest rate. For example, the force of interest delta is given by log of 1 plus I if effective interest is I. Then that is I minus I square over 2 plus I cube over 3 minus I to the fourth power over 4 plus and so on. So when we use the first term only, so delta is approximately just I. So this is 0.05. So suppose I is equal to 5%. If we use only the first term, then delta is approximately 0.05. If we use the first to second term, I minus I square over 2. So delta is I minus I square over 2. So this is equal to the 0.05 minus 0.05 square over 2. So this is 0.4875. And if we use the first to third term, delta is equal to I minus I square over 2 plus I cube over 3. And if we plug in these numbers, this becomes 0.4877. And you can see that the the log of 1 plus 0.05 is, let me see, the 0.04879. So the true delta, that is log of 1 plus 0.05, and this is equal to 0.4, sorry, the 0. This is 0.04. So 0.0. And this is 0. Okay. Yeah, this is 0.04879016. So this is very close. So the 5% is not close enough to this delta, but if we use first to third terms, then this and this are very close. So this is useful to calculate this. And log of 1 plus I is simple, but if the formula is more complicated, that using a Taylor expansion helps. Do you have questions? No?
No.
Okay. So this is useful to approximate interest rate. And I have one quiz. We have one quiz for this. So sometimes the quiz number jumps. I did make the quizzes last year, and it corresponds to last year's the videos. So maybe there's some people that watch the videos for the last year. So just for convenience, that I keep the same number. So video number for the video and the number for the quizzes that correspond to each other. Okay, so yeah, so this is a review on power series. So we don't discuss too much about it, but certainly that it's helpful. Okay, so now that we go back to the force of interest and we do some more complicated examples. So example 1, suppose that the delta of sub t is 0.01 plus 0.02 t. So that means if t is equal to 1, interest rate is 3%. I mean, force of interest is 3%, and the t is equal to 4, the force of interest is 9%. Okay. And if $200 is deposited at t is equal to 1 and $100 is deposited at t is equal to 2, what is the balance at t is equal to 4? So 200 earns some interest and 100 also earn some interest. So we would like to see the balance at t is equal to 4. So at first we think about this $200. Or maybe I ask you what's the approximate value on this. So maybe you can guess the answer, and I give bonus credits for the closest answer. Anyone? So this is a kind of free bonus credits. So even if your answer is far away from the truth, you don't get any negative points.
I'm gonna say $375.
Okay. Anyone else? Sorry?
350.
350. Any others? Your answer should be maybe at least $5 different from any other answers.
360.
360. Anyone else? Maybe one more.
390.
380. Okay, so think about it. T is equal to 1, so 200 and 100 and earn interest, so at least more than 300. And the $200 earns the 3 years of interest, and the initial interest is 3%, and the end interest is 9%, maybe approximately 6% on average, roughly speaking. So 6% of $200 is 6% for 3 years, so the 80%. So 18% of $200 is 18, so 36, right? 36. And the $100 at t is equal to 2. T is equal to 2. What is delta? Delta t is equal to 5%, right? So 5% to 9%. So maybe on average 7%. 7% for 2 years. So 14%. and principal is $100. So 14. So my best guess is maybe 350. But this is just approximation. So maybe 360 is closest. That's possible. Okay, so we start calculating this. So $200 at t is equal to 1 becomes $200 times A of 4 over A of 1. So at t is equal to 4. And $100 at t is equal to 2 becomes the $100 times A of 4 over A of 2 at t is equal to 4. So you can just add up these two quantities, but you have to integrate this. So accumulated value at t is equal to 4 is equal to 200 times A of 4 over A of 1 plus 100 times A of 4 over A of 2. Then what is this? So this is 200 times exponential of integral 1 to 4, the delta r dr. So delta r is the 0.01 plus 0.02 r dr. And plus 100 times exponential of the 1 to 4, 0.01 plus 0.02 r dr. Sorry,
2 to 4.
2 to 4, yes, you're right. So this is equal to what? Maybe I integrate first. So integral, maybe just note, integral of, indefinite integral of 0.01 plus 0.02 r dr is equal to 0.01 r plus 0.01 r square. So you can use this. So this is equal to, so 200 times the exponential of, okay, so maybe I would say this as the f of r, then you can see this as the f of 4 minus f of 1 plus 100 times exponential of the f of 4 minus f of 2. So this is what? This is the 200 times exponential of f of 4. F of 4 is you plug in 4. So you plug in 4. So 0.04 plus 0.16. So that is 0.2. So this 0.2. And plug in 1, 0.01 plus 0.01. So that is 0.02. So minus 0.02 plus 100 times exponential of f4 again, that is 0.2, and minus f2. F2 is you plug in 2, so 2, so the 0.02 plus 0.04, so 0.06. So this is 0.06. And this becomes 200 times exponential of 0.18 minus plus, sorry, the 100 times exponential of 0.14. And this becomes, if you put it in a calculator, 354.47. So we have some compounding of interest. So 350 is our guess, but it's almost in between 350 and 360. So 350 is still closest. Sorry, who said 350?
That was me, Garrett.
Garrett Coletti. Oh, you did the closest answer last time also. Right. Okay, so Garrett Coletti. Okay, so you got 2 points on your bonus credits. Yeah, so quickly calculating the approximate value is important, not only in the exam, but also practically. If your answer is totally off, then that's risky for the business. So it's a good skill. A few years ago, one student has really a good numerical instinct, and he got very close answer every time. That's maybe his talent. Okay, so this is the way to go. And yeah, this is a typical question. So we have another quiz for this one for today. Do you have any questions? Yeah, my initial guess is reflected here and here. So 18% interest approximately and 14% interest approximately, but just it's on exponential. So, the exponential of x is approximately 1 plus x, right? But we have some error because this exponential have the second term, third term, and so on. So x squared over 2 x cubed 3 factorial. So these are ignored. So I underestimated the number. But I think the all answers are pretty reasonable. You have a good sense of numbers. Okay, so the next one. So this is another topic, just a remark on simple interest rate. So simple interest rate starts over at withdrawal and deposit. So for example, so suppose $100 is deposited now, okay, and the some typo. And the $5 that will be withdrawn a year later. How much is the balance at 2 years from now with 10% simple interest? So we think about the time diagram first. So is equal to 0, 1, and 2. And at first we have $100. Then 10% simple interest rate. So 10% interest, simple. So $100 becomes what? $110 at year 1. Then
we take $5 away.
Yeah, then $5 that we take off. Yeah, so I put maybe the negative $5 here, right? So then this becomes 105, right? Then this $105 earn interest. So the answer is $115.5. Like the plus 10%. So it's very strange, right? So because we earn the $10 and then after that we earn the $10.5, even though we, the withdrawn, we have withdrawn $5. So if you did not withdraw any money, then this just 110 becomes 120, right? So only $10, but we have withdrawn some money, but the interest actually increased from $10 to $10.50. So it's very unreasonable, but this is the way to calculate simple interest. So just to simplify the situation. So simple interest, if it does not reset at any withdrawal and deposit, it's too complicated because we have to think about when is the, the baseline. So based on which principle we calculate simple interest, that is so complicated. So our conventional way to calculate simple interest is it starts starts over at each withdrawal and deposit. So that means that if you have a bank account, a savings account, and you continuously, withdraw some money like 1 cent and deposit 2 cents every day, you will get slightly more interest. Yeah, usually the simple interest is used. But anyway, very small difference. Yeah, we have also another quiz for this question. Do you have any questions? So this is logically not consistent, but still, this is the way to calculate simple interest rate. Okay, so the next, the equivalent rates. So for example, the 3% annual effective rate and the 2.96% rate, nominal rate, compounded monthly, have the same result after a year. So in such a case, the two rates are called equivalent. So in general, we define the equivalent rates in this way. So two rates are called equivalent on the interval T1 to T2 if both produces the same interest during the period. So we don't care what's happening between T1 and T2, but just that we compare the amount at T2 and T1, and if we got the same interest, then we say those are equivalent on T1 to T2. So that means that if A1T and A2T are two accumulation functions, then if A1T2 over A1T1 is equal to A2T2 over A2T1, we say these are equivalent on T1 to T2. And of course, the T1 and the T2 are not necessary. Or I would say the arbitrary if interest rate is constant. So when we say annual effective rate of 3% and the nominal rate of 2.96% compounded monthly, so those are equivalent for the time period because we don't specify the interest rates don't change over time. So in such a case, we don't need to mention the time period like this. Okay, so an example, find an annual nominal interest I compounded quarterly, which is equivalent to the nominal rate of 6% compounded every 2 years. So consider the 2 year as a time period. Interest rates don't change over time, so just pick one time period. So consider a 2 year period. So then at first, what is the effective rate for this one? So effective rate for this one is the 1 plus I over 4 to the power 4. This is for 1 year, so 2 years. So 4 times 2. Then what's the next one? So this is this one. And what's the next one? The nominal rate of 6% compounded every 2 years. So that means that we have to wait for 2 years to get nominal rate of 6%. So that means over 2 years that we get the 6% times 2. So 1.12. So 1.1 plus I over 4 is equal to the 1.12 and to the power 1/8. So then I is equal to 4 times the 1.12 to the 1/8 power minus 1. So this becomes 0.0571, so 5.71%. So 5.71%. If this compounds the every quarter, then its nominal rate of 6%. Do you have any questions? Okay, so maybe we finish up the last one. So this is another example for the equivalent rate. So this is but the variable rate. So suppose the force of interest delta of t is equal to 0.05 plus 0.02t. So it's increasing over time. Delta 1 is equal to 0.07. Delta 2 is equal to 0.09. Find a nominal rate I compounded semi-annually equivalent to delta t on 1, 2. So this is, yeah, so changing over time. So we have to specify the period. Then, okay, so nominal rate of I compounded, the nominal rate of I compounded semi-annually. So that means the 1 plus I over 2 and the square, because the 1 year, so 1 year period is the 2, the semi-years. So this is equal to the A2 over A1. And what is A2 over A1? A2 over A1 is the exponential of 1 to 2 delta R dr. So this is exponential of 1 to 2, 0.05 plus 0.02 R dr. So this is equal to exponential of 0.05 R plus 0.01 R square and plug into 1. So this becomes actually the exponential of 0.14. If you plug in 2, 0.14, then minus 0.06 if you plug in 1, 0.06. So this is equal to exponential of 0.08. So this is 1.08, the 3, 2, 9. So I is equal to the 2 times the 1.08, 329 to the half power. You can see that the half power. So you take the half power on both sides and the minus 1 and times 2. Right? So this is approximately equal to 8.16%. So yeah, roughly speaking, this is 8% on average, but to be accurate, this is 8.16%. Okay, so that's the today's materials. Yeah, so if the interest is varying, then to consider equivalent rate, we have to specify the time period. Okay, so that's it. And now that you can start the quiz. I think it's available now. Yeah, actually this is the quiz. So you can go to Canvas and you can start the quiz. And you can ask question by chat or you can just speak up.